Okay, in that case, we'll move on to our next speaker tonight, Richard Knott, who's going to talk about more software and muon counting. Richard, the floor is yours.
Fantastic. Thank you very much. Thank you, Andrew, for the introduction. Um, as Andrew has said, my name is Richard. I am a member of the BAA RAG, and also I'll hold my hand up and say I'm a trustee for UCRA Charity. Over the past year, we, UCRA, have been reviewing our current equipment lineup for recording muons. I'd like to take this opportunity this evening to showcase our work. Um, the question could be asked, something that Andrew touched on, as to why, as amateurs, we do any of this. I think we have a natural curiosity for coincidence. We are good at pattern recognition, and it gives us satisfaction to be able to make correlation between cause and effect. A case in point, the recent X-class flare that I recorded Friday last week using my UCRA VLF aerial and receiver. And my ability to use publicly available data, in this case, GOAS 16 X-ray flux measurements, to establish a correlation to confirm the measurements I recorded. Oh, and we can also provide said data to a monthly publication such as Radio Sky News, edited by John Cook. And it enables us to learn, it enables us to participate, and it enables us to collaborate. So, a quick overview of where we are now. UCRA currently supply the Cosmic Watch derived detectors. We are capable of recording beta, gamma, and muon events. Uses standard BC408 scintillator and a silicon photomultiplier. Data from the photomultiplier is processed by an Arduino Nano clone and made available through the serial port of the Nano or recorded to microSD. To realize the detection of muons, of course, one needs to have two detectors to be able to discriminate the beta and gamma events from the muon events. So let's acknowledge the elephant in the room. There is limited external software available for the end user that can easily take the numbers that come out of the detector and produce a suitable graph for visualizing the data. This can be a hurdle or even a barrier to new users from experimenting with their equipment and subsequently sharing results to the wider community of fellow users and enthusiasts. Reflecting on the clear correlation between the UCRA VLF equipment and the GOAS 16 X-ray flux, is there a possibility of demonstrating correlation between our recorded muon coincident events and other publicly available datasets? The question being, what affects muon count rate? Is there correlation between muon count rate and the sun? I'm very interested in the sun. I do a lot of solar astronomy, and I'd be interested to follow that through. If I use different GOA datasets, proton, electron, or indeed the X-ray flux, as shown at the top here, could I demonstrate correlation? Is there correlation between muon count rate and the Earth's dynamic magnetic field using suitable geomagnetic datasets? Here I've got Lancaster University's Aurora Watch dataset. Or indeed, is there correlation between muon count rate and other recorded secondary cosmic rays, possibly neutrons? In this case, from Finland, from the Neutron Monitoring Database dataset. I'd be interested to find those things out. And what else might we be able to record or detect using a muon detector? As we know, the origins of cosmic rays is not certain. They could originate from supernova events or other phenomena. Case in point, this is a gamma ray burst about 2.4 billion light years away that was observed jointly by two space telescopes. The Niels Gehrer Swift Observatory, that when it was bought in 1999 cost 140 million pounds, for 140 million dollars, and the Fermi Gamma Ray Space Telescope, that when it was purchased in 2008 cost $690 million. And this is from the 9th of October 2022, hence the name 221009. Hubble later confirmed that this was caused by a massive star undergoing supernova that generated the gamma ray bursts. And what about our small ground-based detector, the Muon detector? Can we, or did we, see anything? Well, this is data that has been provided by Mark Prescott in Kent. Mark, I'd like to thank you. It's difficult to see. On the left-hand side of the graph, we've got 12 hours before. On the right-hand side, we've got 12 hours after. The event is highlighted by the arrow. However, looking at average muon count rate, shown in red here, there does seem to be cause and effect, which isn't bad for a 200 quid detector. There is potential for being able to use for other things. And to be able to use it for other things, we need to be able to share our data. How easy is it for us to be able to share and compare our data? It depends on your setup. I have a couple of cosmic watch systems that are configured as shown on the left, with the scintillators as close as possible, i.e. I have a larger area that I'm looking at. The more common setup is shown on the right, where there is a larger distance between the scintillators. If we do try and compare data sets, what additional data manipulation has to be undertaken to enable apples to be compared with apples? Surely we just want to compare our data. And this begs the question, is there things with our current detector that could be done better? I've listed some of the thoughts on the current offering. We know users have taken their detector successfully on Eurostar to record muon count rate under the English Channel, but the data lacks date time when recorded to the internal micro SD card. I have been running my system since September 2023. You can't quite see this, but my OLED displays are completely shot. A known OLED problem: when text is constantly displayed, it will eventually destroy the pixels. You will also notice the interesting count rates displayed on my two detectors, the top detector being the master, showing a count rate of 97.15 counts per second, and the slave showing 15.24 counts per second. I can assure you, I don't live in a highly radioactive field. Others of you may have observed this as well. It's a consequence of the nano's millisecond time function that rolls over about every 50 days and causes these inconsistencies in the dose rates that, or the count rates that are shown on the detectors. So we at UCRA thought that we could bridge these limitations, let's call them that, by inclusion of additional items to the current detector design. Shown here is one of my early breadboard iterations, testing out ideas. The enhancements that we thought about was to include not only a temperature sensor, but also a temperature and pressure sensor using a standard Bosch BMP 280 unit. Bearing in mind people like to go to France on Eurostar and want to record, we've included a real-time clock using a DS3231 system that is button cell battery powered and will enable data that is recorded to the micro SD to include date and time. We have a larger OLED display from which we can display more information and graphical information at the same time. We've introduced some user buttons so that we can make potential changes to the detector on the fly rather than having to recompile the code and upload it. We've looked at a faster, more capable microcontroller unit, in this case here, a Raspberry Pi Pico, readily available, going to be available until 2040. And we've thought about standardizing the scintillator geometry so that when we compare data, we're going to have something to talk about that is the same with everybody. And this is the result. The Picomuon detector, the new Picomuon detector from UCRA. We took the opportunity to showcase at Astrofest 2025 this year to introduce the product and its capabilities to those of you that attended. So let's take a look inside. The unit is designed around two printed circuit boards. The upper PCB, we're calling it the OLED PCB, having all of the I2C peripherals, the OLED, the BMP 280 temperature pressure sensor, the real-time clock, and an EEPROM as well as the user interface buttons. The lower PCB, the main PCB, accommodates most of the electronic circuitry, but also has two overlaying coplanar scintillator assemblies, still nominally 5 centimeters by 5 centimeters by 1 centimeter, that are separated by a standardized 2 centimeter gap. So each detector will have the same geometry. And if we include the front panel onto the front of the unit, we can see that we now have a micro SD card accessible from the front, which we think would be easier for users to be able to access rather than it being on the rear. Turning to the rear, we've got something slightly different. The Cosmic Watch had a single BNC and a coincidence connection. We don't need a coincidence connection because it's all done inside, but we do have the ubiquitous micro USB port to the Raspberry Pi Pico. We will be including a suitable USB cable that will connect to this. You won't have to scrabble about at home to find one. We've also included, we've moved away from BNC, moved over to SMA connectors, that the end user can plug into an oscilloscope or into other detecting equipment that will give pulses for the top or the upper, the bottom or the lower, and coincidence events, so that they could use those in other experiments should they so wish. And the display is going to, because it's larger, be able to give us a lot more information. We've rewritten the microcontroller code in C to reflect the hardware changes. There is a UCRA GitHub repository containing this code that will be made public as soon as we release this product. And the larger OLED offers us much, not just displaying current counts as can be seen on the right-hand part of the screen, the top 27, bottom 47, the coincidence 3, and count rate. Here I've got the top, bottom, and coincidence. But we can display other information as well. And we've got some graphical displays, a histogram of the current Muon ADC values that if you was at Astrofest will have seen. One thing I will state is that the count rate is for the past 60 seconds. So it's the count per second for the last 60 seconds. It's not a cumulative rate that we currently have on the Cosmic Watch detector. So this value will change. Those of you that have had a detector that's run for some time will know that the count rate very rarely fluctuates once you've accumulated a large amount of time. Now, recognizing that this is a big change from the current detector, we have written a comprehensive user manual to accompany the Picomuon detector to support our many users to be able to exploit the full capabilities of their unit. This covers simple things from unboxing to power on, to recording data, various menus that are available on the OLED display, potential errors that may occur while using the equipment and how to remedy them. The unit has a real-time clock that needs a button cell. Unfortunately, we're not allowed to include button cells in any overseas purchases. So there'll be instructions on how to install a button cell and set the correct date time. There's also the possibility of being able to upload new software as additional features appear, or any bugs are resolved, as well as the expected waveforms from the rear of the SMA connector should the user wish to use such facility. And here we can see the graphical display on the right-hand side here of the last 1,000 muons that we detected and what their actual ADC values are. The Pico has a ADC that will go from 0 to 4096. Clearly, if we took some measurements with that and tried to compare it to the current Cosmic Watch, we'll have a difference in the ADC values. So we've taken the decision that we're going to scale the Pico ADC from 0 to 4095 to 0 to 1023, so that there's correlation between the Cosmic Watch and the Pico detectors. Now, many users will, of course, say, I want to tweak my detector settings. And for the current detector, one has to modify the code through the Arduino IDE, recompile said code, and then upload it to your detector. We wanted to streamline that process and to simplify it for the end user. We've implemented a text-based configuration file that can be edited using Notepad, or as shown here, Notepad++. Variables that the user can change are the name of the detector. Fast boot, this will not allow the splash screen or the first information screen to be shown. It will boot into the software a lot quicker. We can change the brightness of the OLED, brightness of the LEDs. Why might you want to do that? If you've got a lab and you've got 10 of these going, you don't necessarily want to have 30 LEDs flashing in your face. And we're also able to change the threshold values for which events would be recorded, should you so wish. The revised text files would then be copied onto a micro SD card, and we are including a suitable micro SD card with all supplied units, inserted into the micro SD card slot located on the front panel of the detector, and then uploaded to the EEPROM via a menu accessed through the user buttons and the OLED display, all covered in the user manual. This provides full user configuration of the unit on the fly. Now, what does the data look like? So, unlike the previous detector, data can be stored on the inserted micro SD card at any time. You don't have to upload any additional code to be able to store to the micro SD. The code will auto-detect an inserted micro SD card and allocate a file name, text, followed by a number, a unique number for that file, and start storing data to the micro SD card. Because of the nuances of the code that it's been written on, you can't just pull the micro SD card out, you have to unmount it. Once you unmount it, it is then safe to remove the card. All the data will be stored on a CSV file. It's similar to what the previous model is, as shown on the top of the screen here. And the CSV file can be manipulated by the user using any software they prefer. Note that the header includes what your threshold value was for both your top and your bottom detector when you were recording. And a simple script to enable users to be able to record data using a single board computer, should you so wish, to get the data themselves and access the data through the USB interface on the Raspberry Pi Pico has been put into the user manual. The date and time here, shown here on the bottom half, is the date and time that would be gained or be got from the single board computer that was actually recording the data. This is not the date and time that comes from the real-time clock. We suggest the use of a Raspberry Pi 4 or Raspberry Pi 5 because it's something simple that we can all get access to and is easy to program in Python. And just as a bit of information, um, similar to when data is stored on the micro SD card, you should expect about 40 megabytes of data per day to come out of your unit. But it's not plug and play. I've got the kit. Now, what does it do? There is an expectation from some end users that any new bit of kit will be, to a certain extent, plug and play. Many of us are not confident in writing our own programs to get, process, and display the information that is available to us through such kits. Many of us don't have the time or the patience required to undertake such a task, and that may actually put us off making the initial purchase of the kit, and that would be a shame. Recognizing this as a barrier to use, UCRA have written a full set of code that will get, process, and present data from your Picomuon detector. The one requirement would be the additional cost of a Raspberry Pi 4 or Raspberry Pi 5 single board computer. Either will do. I've not tested my software on a Raspberry Pi 3 or previous versions because I don't have those. Uh, we are including a full user's manual on setting up the Raspberry Pi 4 or 5 as a headless system connected to your Picomuon detector, as well as a user manual on how to install the actual code to your Raspberry Pi 4 or 5 to exploit the data that you gain from the Picomuon detector. Again, this is all available through our GitHub repository. So let's ask the question, what do I get? Well, what you get is what you see. In fact, the software itself will set up a web server on the Raspberry Pi and create a web page and will populate that web page with graphs such as this. So I'm going to, by the magic of pressing Alt Tab, see if I can get my web page up. Here. This is the web page that will be put onto the Raspberry Pi 4 or 5 and will be populated with the information, the data that comes out of your Picomuon detector. There's a simple menu bar at the top that allows you to navigate around. It's just a single paper. The daily graphs are for the top detector, the bottom detector, and the coincidence events, the muons. And we provide counts per minute, the frequency of counts per minute, and the frequency of the ADC values. Not only do we do that, but I've also written the same code if you've got a smartphone. So at home, when you are connected to your home network, you will be able to access the information from your Picomuon detector via your Raspberry Pi 4 or Raspberry Pi 5 and be able to view yesterday's results on your smartphone, which I think is a bit of a step forward from what we previously had. Let me just go back to here. What else do we have? Well, what about correlation to other public data sets, I hear you ask? Well, there are three additional graphs that we look at this moment. We can look at the daily variation of muon counts, and here I've binned it in 5 minutes, and the percentage daily variation of muon counts also binned in 5 minutes, because I'm interested as to whether the secondary cosmic particle muons and the secondary cosmic particles neutrons have some correlation. On a daily basis, I don't seem to see much. We do it for weekly, and I've got some sort of correlation there, but I'm not necessarily accepting it. And if I've got enough data, i.e. 31 days, I can look at monthly variations and I can see that there is some sort of correlation there, but I'm not wholeheartedly convinced by it. So, is there other data that I might be able to compare against? Well, I am lucky enough to have been running a system for 3 months, for more than 3 months. And I've started to look at my 3 month data. One of my goals is to compare my measured data against publicly available data to look for coincidence. And we can see here in purple is a percentage change of muon counts per day against average muon counts or mean muon counts. And in black is the mean neutron counts. Now, I can see in the middle part of the graph here that there is clearly some correlation that the neutron count has gone down by about 4% and my muon count has equally done about a minus 5% change. But there are clearly parts of this graph that don't follow that trend. On the left-hand side, my muon counts are going up and the neutron counts are going down. So we need to be able to explore these parts in further detail to see what is impacting the muon count deviation from the neutron count deviation. And reviewing papers demonstrates that muon count rate is dependent on the air column above the detector, specifically the pressure and the temperature that will alter the density above the detector and thus impact the number of events the muon will experience while traveling from its point of creation along the path to your detector. And I've only just started working on this, but the Picomuon detector having a Bosch BMP 280 temperature pressure sensor enables us to calculate standard temperature and pressure. And that's what I'm showing here in black. The standard temperature and pressure compared to standard temperature of 273.15 Kelvin and the standard pressure of 1013.25 millibar hectopascals. Again, on the certain parts of this graph, especially on the left-hand side, we can see that there's good correlation between the change in the muon variation and the change in the standard temperature and pressure. But at other parts of this graph, especially around the middle here, I'm struggling to understand what that variation is. And looking further at the papers that were talking about how environmental conditions impact on muon counts, they put forward that we should calculate a barometric coefficient. And I've been able to do that for our detector. What I haven't done at this moment is to use this value here, minus 0.20 percent per hectopascal, to be able to then correct what my muon counts were for that particular pressure range. This value here of minus 0.20 correlates quite well with other publicated values of the barometric pressure. And so this is a work in progress. These last three graphs that I've shown you will be included into the web interface for the Picomuon. It's going to be the next step of the software that I develop for it. So this is a bit of a work in progress, and we will be able to utilize this information to be able to find out if there is correlation between muons and neutrons, or muons and magnetic field, which I will be looking at as well, or muons and the solar events that occur within the sun. And with that, I'll stop and say thank you for your attention. I'm happy to try and answer any questions.
Very good.
Or take a few questions and then let Andrew have a final session. Any questions, anybody?
Yeah, I have, if I may, yeah. Have you left the analog front end the same? You know,
Yeah, so we've got the amplifier and the peak detector is the same.
okay, because I've been doing a lot of thinking about the whole chain on all of this, and even at the beginning of that chain, I still don't understand that rather complex arrangement of diodes on there. But let's park that. I know roughly what it's doing, but I don't understand it well enough to claim that I understand it. And the pulse stretcher is the same, is it?
Yes, predominantly because the ADC, either on the Nano or indeed on the Pico, would not be able to react in the time frame that the pulse would be generated from the SIPM. The SIPM pulse itself is still available via a test point on the main PCB if you were interested in that, David.
Yeah, yeah.
The one that comes out of the SMA connector is the amplified and stretched signal. So that's going to be 2 milliseconds,
Oh,
whereas the one that would come out of the test point would be microseconds.
okay. I mean, there's a whole host of issues here that I got buried in reading about the ADC on the Nano. And it turns out actually with the way they're running it with the pre-scaler on the ADC, that the ADC has nowhere near the resolution that they claim it has. My guess is it's more like 2 decimal digits or a bit less. And this has been studied in other contexts online.
And this is the Nano or the Pico.
The Nano, no,
Right,
well, I was going
okay.
to lead on to the Pico.
Yes.
Now, the heart of the old code on the Nano is that the time cycle is determined wholly by the conversion period on the ADC, how
Yep.
fast you can repeat that, and then how do you then correlate the data between the two detectors.
Yes.
So my line of thinking was, how the hell do we speed that up and then do something rather different? But yeah, I can see the direction you're headed in. I think the other question I was going to ask is, what's the resolution of the real-time clock? Is that only a second?
Yes.
Because
Yes, it
my,
has an accuracy of
yeah,
15 minutes per year.
b-
I'm not going because I'm not going to say that um, s- we put much effort into getting a real-time clock that had a higher
no,
resolution. In fact, there's very few available.
I appreciate that, and I've
Yeah.
looked at that, and then I headed off in a different direction. And my gut feeling is that a lot of the thinking to date has been more about count rates and averages per unit time, and ideally we should have some errors on that, but let's park that issue. Whereas I know for a fact that we're really throwing away a lot of timing information. For instance, the ability to make quite a precise measurement of whether the arrival times of the muons conform to an exponential distribution. In other words, it could really convince yourself that you've got that, and then you can do some interesting background subtraction things. But you certainly can't do it with the existing hardware. So what I was trying to think of is, given that we're almost certainly going to be having an external device, be it a Raspberry 4 or 5 or whatever, and you can put very accurate time sources onto that if you wish, was how could one then use that ensemble to record much more precise timings of each event? And the conclusion I arrived at was that really over the GPIO, for every pulse that the SIPMs generate, you ought to flag something back to the Raspberry, which would then timestamp as in the most accurate way. And I think you could get down to probably 10 microseconds or something like that without trying too hard, possibly better with a more elaborate setup. And I think that's a dimension that really hasn't been studied before. I've read all of the background papers and the, gosh, I forgot his name though, the guy who invented the thing, his dissertation and all the rest of it. And that was the direction I was going in, was how on earth do you have a more intimate coupling between, well, ideally not a nano because that's old kit and way too slow. I'm very pleased to see using a Pico and ideally one of the newer ones, the 2350s or whatever. So
Well, the 2350 could just slot straight into where the 2040
yeah.
is
And the other
because
thing
there's
you
no
do is you
change.
can crank the ADC much, much harder on that. You get better precision and it's much faster. So there's an interesting set of ideas around that. The way I've sort of ended up is that I wasn't convinced it was worth spending any more time trying to analyze what I get out the back of the nanos because I think it's just missing too much. You know, in a nutshell, I've said this
Well,
before in other meetings, I can make a measurement in an hour to about 5% on the rate.
I thought that you would raise this point, David. So that's why I included the graph where I had muon counts per day, and I'm getting about 15,000 muon counts per day. So that's plus or minus about
Yeah,
120, which is
there's
1%.
the
So I'm happy with 1% for the
well,
measurements
but
that
what you're
I'm
doing,
capable of
what
making.
you're doing is time averaging.
Yes.
Let me not labor this, but I won't. One point when I look back through a bunch of statistics books on analyzing, data from particle detectors, I came across a really interesting exercise where they were using the example of the neutrinos that had been detected, the burst of neutrinos from SN 1987A, where you've got a bunch of stuff that came in over quite a short range of time. And they then tested that statistically to see how different was it from noise. And it was way different. It was a really convincing measurement. All of the long-term data averaging completely misses that. You just cannot do any of that kind of analysis. And that was what was leading me to think, is there a way we could work with much more precise timings that would actually leave us sensitive to realistic measures of bursts, if you like, and ones which would be of statistical significance as well. I mean, how you interpret them will be for downstream analysis. The other thing that, given the talk that we had relatively recently, Paul, with the academic who was building those much bigger detectors, he largely dismissed the sort of energy sensitivity, and I agree that's exceptionally difficult. Those shapes of those curves are so shallow. Whether you could do anything or not, I don't know. But that again was leading me to believe timing. I was pleased to see in your code that you've bumped the USB interface up about as fast as you could get it. And with the current Nano, I think it's just wasting an awful lot of time doing completely irrelevant conversions from ADCs to millivolts,
Yeah.
which just give you extra dead time and give you effectively nothing for that, and a more complicated calculation. And then finally, the other point, which I don't know whether you've resolved in the current code, is that the current Nano code hangs around until the tail end of the pulse drops below a certain value. Now, this may be nitpicking, but I think that's formally incorrect because you're building in a dead time bias towards high energy events. And ideally, whatever goes on, I think have a hard cutoff. Just make a measurement over a defined time interval, and then you won't bias anything. You may be able to correct for other things later, but don't incorporate a bias. Now, I suspect that they got away with it because essentially we're very insensitive. The rate drops off so fast, and the rates are very low, so probably you could never tell. But I think it's formally incorrect to do that.
We do still do something like that because the Pico's ADC is faster than the Nano's ADC. We've
Yeah.
had to implement a um, reset threshold, which we're setting at half the value of the event threshold, so that it's because it is able to keep it can do two reads in the time that the pulse is still high.
Yeah, they're
Um,
much better beasts. Yeah, yeah.
so we have had to put that in. Um, what I would like to do is to make two measurements so that I can get an average of the ADC, um, which would be more informative because I'd like to know that I'm able to,
Ah, okay. Well,
so I get because I don't know whether the ADC is measuring on the rise or on the start of the
well,
fall.
I thought about that, and my solution to that was to have a fast circular buffer where you just there's so many measurements, and you just kept reading until it generated something above threshold, and then triggered.
That's effectively what we're doing because it takes 96 cycles, clock cycles at 148 megahertz. So it's 2 microseconds to physically take an ADC measurement. Um, and that's just about fine for being able to make a coincidence event. Um, and with the hardware that's on the Pico, we accept that there are challenges with the Pico's ADC that at 511, 1535, there are known um, high points, and we've excluded those from the software so that their data isn't recorded at those three particular ADC values because of the known transition between
Oh,
a low,
this is just hardware problems in the
yeah, it's
Pico. Yeah,
hardware
yeah.
problems with the Raspberry Pi itself rather than with our code. So,
Sure. Yeah.
so
Okay.
Yeah,
that's a known problem. That is built into what we've thought about.
Okay. I think guess the final point I would make is that if the line of thinking I was having was that if you could get the accurate timing, then essentially my thinking was you just shovel data independently off both detectors as fast as you can and do all the correlation in software downstream, which
Yeah.
has which has the benefit that you can then do background analyses in a much more powerful way. Uh,
Yes. And as I said, the SMA connectors are the amplified pulse and the stretch pulse, but on the board itself is still, so if you take the back panel off, you can still got two test points that are right
yeah,
next to
yeah,
the
sure.
SMA that are the
Yeah.
raw SIPM readings that
Mm,
I use for when I'm testing the units.
yeah,
So you've got that ability, should you so wish, to then extract that information directly from the detector and not use
yeah,
any of the
okay.
software that's there.
Yeah,
Just use the fact that we've got you'd use it's a very expensive high voltage supply, 29 volts to the SIPM, but it would get it going.
yeah. Oh gosh, what I was going to say next. It's completely slipped my mind now, the final point. No, I'll park it. It'll come back to me. Thanks. Yeah.
Okay. Any more questions? I think I might call time on this one unless it's a really burning question and let Andrew finish off for 20 minutes and
Yeah,
before we
I,
finish.
I I do have one question, which is, I think, extremely simple after that rather complicated discussion, which is, would it be possible to include on this new Muon detector a little button on the front which turned the display off? I'm just thinking about that business of
Oh yes, sorry.
displays dying over a period of time.
Sorry, Andrew. Yes, that is one of the functions. It will turn the OLED off. Yes. And
So
then you just press any of the buttons and it will re-bring the display back up. I haven't got one at hand to be able to show you that working, but yes, it was one of the requirements of the software that I wrote.
okay.
Yeah,
Um,
that is the great advantage of the new one. It has buttons.
I
Um,
have uh, I have one final question related to the last topic about the ADC on the RP2040.
yeah.
We know yeah, we know it's faulty. I was the first person to actually discover the differential nonlinearity error on the ADC. But do you actually get real ADC histograms from the device? Because my understanding is that these these detectors don't actually detect the energy of the incoming muon in any way at all. It's all
No,
about the crystal.
yeah, okay, Tony, I accept that. And as David said, it's very difficult to be able to measure energy. If I wanted to measure the energy of the muon, I'd want to stop the muon and get all of the energy out of it. I'd need a scintillator that was possibly 150 centimeters thick to be able to stop the
Wow.
muon.
Okay.
I'm not going to be able to do that. So,
Unless
as I
somebody
said,
wants to come up with some money.
well, if somebody wants to come up with some money, you won't be able to do it because you can't buy scintillators that big. As I've said to Paul, the ability to measure energy is really a non-starter uh, for what the setup that we've got. We'll just assume that the energy of the muon that is impacting on the Earth is around 3, 4 giga electron volts. And if we're lucky, it's going to be a vertical one and it will deposit quite a bit of energy and I'll get an ADC measurement. What I'm more interested in is seeing a Poisson distribution for ADCs so that I can know that I'm reading a range of ADC events, i.e., there is a range of energy that is being deposited in the scintillator that is generating light photons that are picked up by the photomultiplier tube, and that I haven't got some sort of duff piece of plastic, or that I haven't put my photomultiplier tube onto the scintillator incorrectly.
Ah,
So
right.
yeah, I'm not going to use ADC values to give energy. And that's why I've done no conversion of ADC to millivolts. Um, it's just all I was interested in is what's the shape of the graph that I get? Does it look right? Is it a Poisson distribution? And if it is, I'll tick that box and I'll move on.
Brilliant. Okay, thanks very
Yeah.
much.
It also gives you some comfort that it's actually working. and you can see it from day to day, and it's working consistently.
Yeah.
Actually,
I think that's
you can invert that argument, and the thought I had was, given that the energy distribution is so shallow, the muons are minimum ionizing particles. To first order, they all leave the same signal. So I was thinking, okay, use that to calibrate the ADC.
I think that's an interesting point, David. I think I'm going to have to look through a few theoretical physics books and see what the ionization events are per muon interaction
Yeah,
with
I think the
plastic, and
statistics are
then
going to spread it so broad it's almost meaningless. Yeah.
if anybody knows how to do any Monte Carlo calculations or Genk calculations, please get in contact with me through Eucra. I would be more than happy to talk to you as to what I would like so that I could actually work those things out.
Yeah, I remember what my final question was. If anybody here or anybody on here can find somebody who really understands what that diode arrangement does at the front end, I'd be really interested to see that documented.
Okay.
don't look at me.
Well, I've found similar examples in Horowitz and Hill.